In this episode, let's tear down and repair a very crusty but extremely powerful neodymium YAG laser. I bought this off of eBay some time ago. This is the handpiece assembly of a tattoo removal laser, and I scored this as spares and repairs for a little under 30 bucks. These are Q-switch giant pulse neodymium YAG lasers that are capable of obliterating tattoo inks, which are highly absorbent to 1064 nanometer laser light, while leaving the skin relatively unharmed. I refurbished one of these over a decade ago and posted about it on the 4HV forums. Anyway, this thing rattles a bit, and I suspect a blown flash lamp, so hopefully there's not too much damage, so let's get it apart. So I have the laser assembly out of the handle now, and we can take a look at the internals of this thing. In the middle we have the cavity. This is internally a reflective cavity that contains the neodymium YAG rod and the laser flash lamp. This is the rear mirror mount for the laser that contains the high reflector. This design is actually very common on all of the Chinese tattoo lasers that I've seen, and it comprises of a circular mount that's actually aligned by these 4 screws. These 4 screws are actually all fighting against each other. So we've got 2 screws here for the vertical direction, which sort of press against the chassis, and then we've got 2 screws side to side that are sort of tapped into the chassis. It's a really terrible design, and it must be a real pain in the backside to align this correctly. Really, in a YAG laser such as this, we should be using a proper kinematic mirror mount. And when I come to strip and repair this, because I want a benchtop instrument essentially, I'm going to replace this mirror mount with something more sensible. This is a view of the front of the laser, and we'll notice that there is no mirror mount at all. There is a mount on the front of here, but this is for mounting external optics like focusing optics or frequency doubling optics. But yeah, no mirror at all. The mirror coating is actually deposited on the front surface of the neodymium YAG rod. I think this is to aid in the ease of alignment in manufacture. If you think about it, if we already have a mirror coating on the rod, we can be fairly certain that that mirror is already aligned, and so the only mirror that has to be tweaked during the manufacture is the rear mirror itself. In between the rear of the rod and the high reflector is a black crystal. This is actually the Q-switch. This is a chromium YAG saturable absorber, and the idea behind this is it allows power to build up in the cavity before suddenly dumping it. We'll take a look at a diagram shortly to explain really how this thing works. On the subject of bad design, another modification I need to make on this is to improve the clearance at the end of the lamp here. This is the electrode for the lamp. Now, the lamp will be provided with about, somewhere in the region of 800 to 1000 volts or so. And the clearance, even at that, is too small. We're looking at maybe 4 millimeters here between the end of the lamp and the chassis. On top of that, in order to fire these lamps with a water-cooled assembly like this, we actually need to send a trigger pulse down the cable as well. And that'll be somewhere in the region of, 5 or 6,000 volts perhaps, which would be easily enough to jump from the end of the lamp to the chassis, especially in the case of a lamp failure. So what I think I'm going to do here, another modification as well as the rear mirror mount, will be to mount this on the mill and mill out a section here just to improve the clearance between the electrode and the chassis. Here's a diagram that shows the basic setup of the YAG laser cavity. We have a neodymium YAG rod with a partial mirror coating on one end, which serves as the output coupler. As I've said previously, I think the manufacturers of tattoo lasers do this to simplify the design and alignment. On the left, we have a high reflecting mirror which forms the other end of the cavity, and between it and the rod, we have a chromium YAG passive Q switch. Mounted to the side of the laser rod is a flash lamp. In order to power this correctly, we need a large capacitor with a storage capacity of a little under 100 joules for this particular laser, and an inductor to control the discharge rate of the capacitor. This is called a pulse forming network. The speed of the discharge needs to be closely matched to the specifications of the flash lamp and the fluorescence lifetime of the laser. In this case, it's about 200 microseconds, which is well matched to the neodymium YAG's 230 microsecond fluorescence lifetime. For simplicity, a switch is shown in this diagram. In reality, the lamp will be triggered by means of a high voltage trigger circuit. The capacitor is charged up to around about 1000 volts, and this stored energy is discharged into the flash lamp when the switch closes. A fraction of this optical energy pumps the neodymium atoms to a higher energy state. After a short time, some of those atoms will begin to relax back to the ground state, releasing photons, but the system cannot efficiently laser as the Q switch is currently almost opaque. At a certain threshold, enough photons are present that they raise the chromium atoms to a higher energy state. This allows yet more photons through, an exponential increase ensues, rendering the Q switch very suddenly transparent. This effectively releases all of the stored energy in the neodymium YAG rod in a very small time frame, a few nanoseconds, resulting in a gigantic pulse of energy. Anyway, let's get this thing apart and see what we have. Now that we have the cavity out, I can extract the lamp and the rod. Since I know that the rod has an output coupler mirror coating on it, it would be a good idea to mark off the end of the rod holders so that when I come to reassemble this, I put it in the right way round. I have the laser rod and the flash lamp out of the cavity now, and we can take a look and see what we've got. We can see some corrosion on the rod holders at the end here, some kind of deposit, probably calcium or something. This has evidently been run with tap water. These things should always be run with deionized water because otherwise the aluminium corrodes and all sorts of nasty stuff happens. But it looks, it's unbroken and it looks relatively clean. Very, very nice. The flash lamp as well, there looks like to be some discoloration on there, but it actually looks like it's probably in serviceable condition. Again, there's a buildup of some kind of gunk or film on the surface of the lamp, and I'll clean this off with some isopropyl alcohol before reassembly. I have the end pieces off here, and this is actually pretty interesting. One side doesn't show too many signs of corrosion, although there's some obvious white buildup of aluminium oxide on the inside there, so this all needs to be cleaned out. The O-rings look reasonable. I might replace them. This one is terrible. It's absolutely full of gunk, so it just comes off on my thumb. This is absolutely disgusting. So this needs very cleaned out. It's very, very ill indeed. I think a little wire brushing with a Dremel attachment will get rid of most of that stuff. But yeah, we can't really expect a laser to work well with this kind of grot floating around in the cavity. This is the inside of the cavity reflector, and this is in particularly poor shape, it has to be said. This is responsible for coupling as much light as possible from the flash lamp into the neodymium YAG rod. If I look down the barrel of this thing, internally there's some scorch marks on the internal surface. It looks kind of blackened. There's some cracks in there. Some of the material's actually starting to erode away at the edges. So this has been really abused. That being said, I think if I run a cleaning cloth through it real quick, we should at least be able to reassemble this thing and get it to laze. But I think what I'll do is I'll have a look on the likes of AliExpress and see if I can, you can get parts for these things, right? So I should be able to pick up a new cavity reflector off of there to do a proper job of refurbishing this thing. I have everything cleaned up as well as it can be. The rod especially has turned out very, very nice. All of the grot and detritus has all been removed and it appears to be in very good condition. There doesn't appear to be anything wrong with the reflective output coupler or the rear coating. It looks just fine. The lamp has cleaned up very, very nice indeed. It does look indeed as if it's the cavity that we have a problem with. I have cleaned this out as well as it can be, but honestly, we're going to lose quite a bit of light into the reflective material as well. So, but I suspect it'll laze. I think we will have enough light coupled into the rod to get the thing to laze. The Q switch itself, also in very good condition. Don't appear to be any problems there. I've hugged out a section of the chassis there with a mill, just so that there's a little bit more clearance between the end of that flash lamp and the chassis itself. Anyway, let's get this thing reassembled and we'll see if we can get first light out of it. I have the laser largely reassembled now. The cavity's back in its sled. I've got the Q switch here, but I'm actually going to replace that last. And I have this god-awful mirror mount. What I'm going to do with this is take the mirror out just now and glue it to a kinematic mount. I've glued the high reflector to a little 1-inch Newport mirror mount, and this should be ideal for aligning the laser. These can be had relatively inexpensively off eBay if you look hard enough. In order to use this new mirror mount with the laser, obviously we need some kind of base that we can mount the laser to and the mirror mount to. And so to that end, I've manufactured a new base out of a nice thick piece of aluminium. I've drilled a couple of holes here, which match up with 2 holes I've drilled in the base of the sled and tapped. I've got a hole for the rear mirror itself, and then there's this section that I've hogged out with the mill. The reason I've hogged this thing out is when you assemble the laser, you can't actually perform any alignment at all with the Q switch in place because the Q switch is opaque and you can't see the reflected beams back off the rear mirror, and so you're kind of stuck. So what I've done here is hog the section out so I can remove the Q switch, perform an initial alignment so that everything's good, and then once that's working we can replace the Q switch and hopefully everything should function as it should. So here's the finished laser assembly. It's all mounted on that nice solid base. There's my rear mirror mount, and the hole at the bottom precisely matches up with the bottom of the laser so that when it comes time I can insert the Q switch. So I have the laser set up on an optical bench here, and pointing into it I have a visible laser. What this does is it shines the beam right the way down through the length of the cavity, off the rear mirror and back out again, and we can see the reflection from the rear mirror on the front of the laser here. All we have to do real quick is just tweak the mirrors until those spots are reflected right back into the laser. And that is around about it. With a short cavity like this and such a wide bore, any rough alignment will be close enough. If it's going to laser at all, we'll get some light output. So let's fill this thing with water, talk about power supplies and see if we can get first light. Before we do anything else, a quick note on safety. Please don't attempt to replicate anything in this video unless you already have a great deal of experience with high voltage and high powered laser systems. That being said, I know that some of you are avid experimenters, and so my advice is always invest in a proper pair of laser safety eyewear. Don't cheap out on this stuff, don't buy stuff you find on eBay. Go and buy some certified eyewear from a respectable seller such as Thor Labs, for example. In order to drive the laser I needed a capacitive discharge power supply, and for this I've actually rolled my own. I saw this case show up on eBay one afternoon and I knew the moment I saw it that this was going to be the case for this power supply project. On the front panel here I've got my high voltage out, so this is internally connected up to a 100 microfarad capacitor that can be charged to 1,500 volts. So you're looking somewhere in the region of about 100 joules can actually be discharged into a flash lamp, which is a very significant energy. Once again, you know, danger high voltage. If you were to touch the output terminals of this while it was charged up, it would very likely kill you. On the front panel here, I've got a key switch so that only I can operate the machine. I've got a potentiometer so I can vary the output voltage between about 600 volts to about 1,500 volts. I've got the power on switch, and then the trigger button is actually hidden under this little missile switch cover so it can't be accidentally discharged. We'll just take a look at the inside of the power supply real quick. On the left hand side here is the pulse forming network. Here is a 100 microfarad capacitor that can be charged up to about 1,500 volts. I've got a 44 microhenry air cored inductor, and this forms, like I say, the pulse forming network, and its purpose is to slow down the discharge into the lamp so we don't cause it to explode. And you know, we can closely match the lifetime of the lamp to the fluorescence lifetime of the YAG rod. To actually charge up the capacitor, I have a homemade ZVS driver here with a homemade transformer. This transformer has been set up in such a way that its maximum output voltage is about, you know, a little over 1,500 volts or so. Triggering the lamp on this is quite tricky because the lamp itself in the laser head is actually surrounded by water, so we can't very well wrap a wire around it and apply a high voltage pulse as we might do in a photographic flash. So what I've got here is a series triggering circuit. We've got a little 10,000 volt power supply that charges up some capacitors and discharges its energy through a very small transformer that's in series with the output of the pulse forming network. And essentially when we press the trigger button, we get a little high voltage spike appears across the lamp, and it's just enough to ionize the lamp and cause the discharge to start. I have the laser here connected up to the high voltage power supply. Currently it's switched off, so we're all good. What I've done here is, because the laser expects to be water cooled, I've actually filled the cavity with deionized water. I'm not bothering flowing the water around because for these short tests it'll be just fine. There's enough thermal mass in there to get rid of any heat. As I said previously, the Q switch is actually removed because I can't complete the alignment with the Q switch present in the cavity. Let's power this thing on and we'll have a look at the output. So we're just charging up now. We should get a little over about 800 volts or so. I have a graphite beam stop in the beam path. This is to catch the beam so it can't go off into the rest of the lab and do any damage. In order to see the beam, assuming that everything works out okay, we'll put a piece of black card in front of the graphite, And when we fire the laser, if all is well, we should get a mark on the card. Excellent. So there's a tiny little mark and a puff of smoke. We can see that the alignment's off a little bit, so I'll move the card and tweak the mirror mount and just repeat until I get a nice circular pattern. So we're getting closer. It looks like we're quite a way off on the x-axis. Excellent. This is working out very well. Oh, very close now. Oh, nearly there. Look at that, that's almost a perfect circle. Excellent. Absolutely fantastic. This is great. The beam quality looks really quite nice indeed. I've installed the Q switch in the laser now, and you'll notice that the view through the camera has changed. This is because the camera is also wearing laser safety glasses. When you Q switch a laser, you can increase the peak power by several orders of magnitude, and this is not only enough to destroy human vision, but also to destroy camera sensors as well. Anyway, let's fire this thing off and see what happens. Nice. If we take the energy from a high energy laser like this and focus it into a point in the air, it is possible that the photons generate such a huge electric field in the air that they cause the air to break down and generate a plasma. Very, very nice. I have a nonlinear crystal placed in the beam path, and so if everything's set up correctly, this should double the infrared 1064 nanometer light to 532 nanometers green. Excellent. It's not really science until you measure things, so I've got a pair of sensors here in order to perform a measurement. On the left here I've got a pyroelectric Joule meter. This you actually hook up to an oscilloscope and it will output a voltage that's directly proportional to the energy in the shot. Because this doesn't measure in the time domain, and I also want to work out what the peak power is, I have a fast photodiode pointed at the surface of this as well, so it can catch the reflection and make a determination of how wide the actual pulse is. If we take a look at the oscilloscope screenshot here from the energy sensor, we can see that we have a voltage of 1.65 volts out, and if we take that figure and divide it by the sensitivity of the Joule meter at 13.72 volts per joule, we arrive at a final figure of 120 millijoules, which is fairly respectable. I suppose I could push this laser a little bit harder and maybe get a quarter of a joule out of this thing. If we were to be naive about this and just assume, maybe a 20 nanosecond pulse width, we could take our 120 milliseconds and our 20 nanoseconds and plug it into an online calculator and arrive at a peak power of around 60 megawatts, which would be very, very nice. However, there is a lot more to this tale. If we take a look at the output from the photodiode, we can see an initial pulse, which is the EMF from the flash lamp firing, and then curiously we've got 5 pulses. I expected to see only one of these, but there are indeed 5, and it doesn't matter how many times I repeat the experiment, I always get 5 short pulses out. If we zoom in on those pulses, we can see that they're each 20 nanoseconds, and so this is most assuredly the Q switch firing. I suppose the correct thing to do now would be to take our 120 millijoules and divide it by the number of pulses. This gives us 24 millijoules per subshot, and if we run this through the calculator with a 20 nanosecond pulse width, we end up at a final figure of 1.2 megawatts. Still very, very respectable output. If we reason all this stuff out, we can work out why it is that we're getting 5 short pulses instead of 1 giant pulse. If you recall, the duration of the pulse forming network is set such that the flash lamp will be lit for about 200 microseconds, and those 5 pulses occur within that time frame. So what happens is, the YAG rod is pumped by the flash lamp, the Q switch eventually reaches threshold and fires, but the rod is still illuminated, and so it pumps the rod right back up to threshold again, and the cycle repeats. I suppose if I was to redesign the pulse forming network and get the flash to be, maybe under 100 microseconds, we could get a single giant pulse out of this. I'm not sure how well the lamp would cope though. Really, if you want good control over solid state lasers, you should use an active Q switch, for example a Pockels cell. This project has worked out much better than I expected, especially given the state of the cavity of the laser. With spare parts on the way, this opens up the possibility of some really interesting high-energy experiments, including experiments with different gain media, for example this Neodymium cerium YAG rod that's just turned up today. I should be able to do experiments with laser-induced breakdown, practical nonlinear optics, and the pumping of dye lasers. As always, a huge thank you to my Patreons, channel donators and subscribers. Your support makes science and engineering videos like this possible.